Welcome back to our plasma class. So, what we are going to study today is something on this scattering in plasma. But before that, what I would like actually, I'd like to tell you something more details on the basics of electromagnetic waves in plasma, plasma equilibria, and plasma temperature. Why I want to do so? Because in the last class I have explained you the things, but what I feel actually some of the mathematical steps that I have used there, you may not be very clear because they are having some skipped steps, and what I want actually I want to make them clear in this lecture. Okay, so we start. So here is what we learned in our previous class on the propagation of electromagnetic waves in plasma. And what we see that we have used a coordinate system, right-handed coordinate system, and in that the electromagnetic wave was propagating in the x direction. So electric field was pointing in the y direction, and your magnetic field was pointing in the z direction. The wave was propagating in the x direction. So you can look at my cursor, the upper right figure, whatever is there, that is showing the picture. Now, as I told you, actually we have two things over here. One is electromagnetic wave that has a speed very high, and you know that electromagnetic wave propagates in speed space, that is speed of 3 into 10 to the power 8 meter per second. And here the particles are moving at a speed which is much lower than that. So that was the basic criteria, basic your fact that you have used in this derivation. So this one actually dx dt is basically the particle velocity, and c is the speed of light, and what we have used the approximation that dx dt much less than c, that is basically electric field by magnetic field. Okay. Now what we did actually, we wrote the particle motion, the charge particle motion in components from for this kind of configuration, what is shown on the upper right corner. Now what we did that x component of force that we have equated with q v cross b, that is lying on the in the your x direction, and then we have written the y component like this again, that is q e plus v cross b, because e is pointing in the direction of y. So that is why E is coming, otherwise this is the component from V cross B, that is dx dt and B, and the cross component of that is pointing in the y direction and with a negative sign. So you know that how to find out the components. You can apply a right hand rule, and you just see that V cross B pointing in which direction. So in this case what was happening, this B, it was dx dt and it was in the direction of x, right? So this is V in this direction, and V cross B, when you do that, B is in this direction, so it is pointing in a negative y direction. So that is why this negative sign has come, and we have used the charge value as q, right? And you know that as we are always telling that electrons will be responding very fast compared to the heavy species, and if something is oscillating too much, then just the heavy species like ions, they give up, and but the electrons, because being light, they follow that, and so that this q later on in this derivation we will be using q equal to E, the charge of electron. So you see that V cross B is giving a negative component here, and QE is the force that is applied on the positive y direction. That is why m dv dt, that is d2y dt2, the y component of motion gets this value. Then when you go for this z direction, you know that already in the direction of the magnetic field, no force can arise. So that is why it is just 0 over here. There is neither electric field is there, neither V cross V any component, because V is in the x direction, and your V cross V will be, what is that actually? Yes. So this V cross V will have this x component and y component. It will not have in any z component of motion in this case, and the particle was propagating in the x direction. Sorry, the electromagnetic wave is propagating in the x direction. So the equation of motion basically comes to be like that, right? So then what we did actually, we told that let us assume that electric field is like this, E equal to E0 cos omega t. Now when you tell that, it is fine to take that, and then we derived the second equation m d2y dt2, and we found that we can approximate it to be like this, right? This is fairly enough, and because v by e, and when you is equal to 1 by c, and dx dt by c is very much negligible compared to 1, right? So we can just neglect this part, and then you just left with q e by m, that q E0 cos omega t by m. And then if you integrate it, then you are getting that dy dt is equal to, just you get an integration, and this is the thing. Now the issue is that in the next step, what we did actually, J is equal to NEV. So J is the current density in the y direction, and that is Ne into dy dt, and dy dt just in the previous slide what we obtained, dy dt is equal to q0 by m omega into sine omega t. Now we have just used here, and we got that J is equal to this one, and on the other hand we also know that J is equal to sigma E, and we compared these two, we got this equation. But here is the issue, then how J is coming to be J n square by m omega, and many of you have understood already that how it is coming. So but many may not have understood how it is appearing to this exact expression. For that actually what I will do, I will derive these equations in a more convenient form, so that it becomes clear to everybody. So I come to this like this. So here what we have assumed, that the electromagnetic wave is propagating as E equal to E0 e to the power j omega t. Rest of the things are same, but only thing is that in your this thing, what you call electric field, I have assumed to be like this configuration. So it is always possible to write it in this form, and if we do so, then you know that dx dt, this expression, the second equation, it comes to be like that q is 0 by m e to the power j omega t. So when you then integrate, it becomes the j omega comes down because of that integration, and you are left with q is 0 e to the power j omega t divided by j omega m. So if you multiply top and bottom by j, j square gives you -1, and then this j e by m omega, because e0 e to the power j omega t, that basically forms the E. Now we come to the next one. You see that J is equal to Ne dy dt, and dy dt what we got previously, that is minus j e by m omega. What we will do actually, we will just substitute this in the expression here, dy dt equal to minus j e by m omega, and what we are getting, that j n square by m omega into E. Now if we compare with j equal to sigma E, we can very clearly find that j is equal to minus j n in square by m omega. So this is the place where earlier confusion was there, how we are arriving to this expression of conductivity, and now you are clear that how it is coming. And earlier case also it was correct, but only thing you have to apply your insight into that, and then you will get to this value. Now, regarding the conductivity, we have arrived to this expression sigma is equal to minus j n square by m omega. And what Maxwell's equations gives us, we have used two Maxwell's equations. One is curl E is equal to minus of del V del T, and the other one is curl B is equal to mu 0 J plus mu 0 epsilon 0 delta E del T. So both of these are applicable here, and as you know, Maxwell's equations are always valid. You can take this one, curl E equal to minus of del V del T, and then you put the value of B. So what we have assumed, the electromagnetic field E equal to E0 e to the power j omega t and B equal to B0 e to the power j omega t. It has to be like that. So if we put it over here and then if we integrate it, then what is coming? It is coming minus j omega B0 e to the power j omega t again. So you are getting just minus j omega B. So what we get finally, curl E is equal to minus j omega B, and you know that everywhere there are vector signs. I am just omitting that for you assume that they are there. Now curl of B, the second Maxwell's equation, is giving you mu 0 j plus mu 0 epsilon 0 del E del T, right? So j is equal to what? J is equal to sigma E, right? J is equal to sigma E. So what we have done over here is, I think again there is J should be here and mu 0 should be here actually. J equal to sigma E, so mu 0 sigma E should be over here, and then mu 0 epsilon 0 delta E delta T E0 to the power j omega t delta T, and you get again j omega comes out and you get this one. Now this sigma is j n square by m omega, what we got here. Now if we just plot this over here and put it over here, then here in this expression one mu 0 is missing. This mu 0 should be over here, and you take this mu 0 over here, you assume although it is missing over here, you just put this mu 0 here, and then mu 0 omega and epsilon 0 E, if you take out, then this part gives you just 1, and here you are assuming that this mu 0 whatever here, it is actually got missed here and missed here as well. So you assume that it is there, then you just take out this j omega mu 0 epsilon 0 into E out, then this part gives you 1 which is coming over here, and this negative part is there, and j anyway you have taken out, so it is giving you n square because it was having no epsilon 0 and you have taken epsilon 0 out. So this is giving you m omega square epsilon 0 over here, and then this is the thing actually. So 1 minus n square by m omega square into epsilon 0. Okay? So this is what you are getting. Curl B is equal to j omega mu 0 epsilon 0 E taken out, then within the bracket 1 minus n square by m omega square epsilon 0. Now what you do actually, you come back to this equation, this first equation, curl E is equal to minus j omega to B. Now you take a curl of this one, curl of E, then this side curl applies, and what you get, minus j omega into curl of B, and then what you get actually, this you expand this one, so it is curl of E, so it is basically gradient of divergence C minus del square E. Now that on the right hand side is minus j omega and curl V multiplied by, and this curl B expression we have just got here. What is that? Curl B is equal to j omega mu 0 epsilon 0 E into 1 minus n square by m omega square epsilon 0. Just put it over here. So what you got actually, this is j omega curl b, j omega remains here, and curl b is just coming from here to here. I've just taken it down, and then you know that if we multiply j into j, that will give you j square, that will be giving minus 1. So this minus and minus cancels out, and then what you get, omega into omega omega square and mu 0 epsilon 0, this part. You know, this mu 0 epsilon 0 is 1 by c square. So that is the speed of light, then E is there, then 1 minus this term. We have already derived that, this plasma oscillation frequency. And if you look it very closely, then you will find that this plasma oscillation frequency is already inbuilt inside this term. How? You see that n is square by m epsilon 0. What is that? That is nothing but square of plasma oscillation frequency. So what we will get out of it is that it will be, I will come to the next page, but before that let me tell you that as usual we know that divergence of E is basically rho by epsilon 0. Now if the situation is such that we are considering length scale which is much greater than the Debye length, then this divergence E equal to rho, whatever the charge density, that will be equal to 0 because of macroscopic charge neutrality, and we can drop this term. If that is the case, then this side only minus del square E is there, and such situation is relevant in many cases like propagation of electromagnetic waves through ionosphere and many more such applications. So on the left hand side, in that case we will be having this minus del square E, but it is not necessarily that this term will be 0 in all the cases. You should remember, depending on cases, this term may not be 0. Okay. Now we come to the derivation part. Then what we had in under the consideration that divergence E equal to 0, then what we get is minus del square E on the left hand side. On the right hand side, what we have actually minus j omega into j omega. As I told you, this will give you plus 1, and then omega square mu 0 epsilon 0, that will give you c square, and then inside 1 minus this n square by m omega square epsilon 0. The plasma oscillation frequency, as we are telling, that that will be omega p square is equal to n square by m epsilon 0. So we just get it over here, and then what we get actually, we get omega square by c square 1 minus omega p square by omega square. So this is del square E, minus sign was over here, and this was plus, so I take the minus sign on the right side, and I get omega square by c square 1 minus omega p square by omega square into E. So that is equal to gamma square E. So gamma square, what we are having is equal to, if you compare this side and this side, then it is coming minus omega square by c square into 1 minus omega p square by omega square. Now that if that is the case, you look very closely to this term and you can see that this can be both positive and negative. When it is positive, you can understand that when it is positive, when this side anyway negative sign is there and this side has to be negative to make the total quantity what is there on the right hand side to be positive. And in that case, gamma will be real obviously. But if that is not the case, suppose it is negative, it is positive. When it is possible, so it should be less than, this side should be less than 1. Then what is there? This 1 minus something which is less than 1, it will give you positive thing. So this gamma square becomes negative because this side is positive and this is negative. The total quantity becomes negative. So square of a negative quantity will give you the imaginary quantity, right? So that in that case it may have a solution of alpha plus jk kind of thing, gamma. So this is a general kind of solution. When this part is 0, this is real, and when this part is, it is purely imaginary, or otherwise it is a complex quantity. Now it is alpha plus jk kind of solution. So now when it will be positive purely when omega square is less than omega p square. Then you see that this side is more than 1 and this is giving a negative quantity, negative into negative becomes positive and gamma become real. And when this omega square is greater than omega p square, always it is negative and the gamma should be a purely your imaginary term, square root of negative, right? So what we get here, the solution as gamma square, del square is equal to gamma square into E. We come back to the previous one for, see this was del square E and del square is equal to gamma square E. See this is the quantity that we got. Now what we are trying to understand the solution of this equation, and that will depend on what is the behavior of gamma. Now we come here, so this is the gamma and general solution is gamma is equal to alpha plus jk. So when gamma square less than gamma square greater than 0, then you are getting a real quantity gamma, and then you are getting solution kind of C1 e to the power gamma x plus C2 e to the power minus gamma x, and you know that this you have to neglect, because otherwise this will keep on growing. So this is a realistic solution, but so it is a attenuating behavior with x, and this says that the wave cannot propagate. So it means that if omega is less than omega p, only in that case you are seeing that this quantity is positive. So then gamma becomes positive and real. So then we see that the wave is getting attenuated exponentially and the wave cannot propagate. On the other hand, when gamma square is less than 0, that is when omega square omega is greater than omega p. So in that case, this is negative and gamma is complex. So in that case, you are getting gamma is purely imaginary if omega is greater than omega p, and let us say that gamma is equal to alpha plus jk, alpha is 0, so it is gamma equal to jk, basically the imaginary part only. So the wave is propagating with a wave vector k, and you can understand that the phase velocity is omega by k, and k in that case is what? Because it is purely imaginary, and k is basically omega by c 1 minus omega p square by omega square square root. So that is the value of k, and because that is the part, imaginary part k, and jk, gamma is equal to jk, then it is coming. So this imaginary part k is coming to be omega by c square root of 1 minus omega p square by omega square. So if you divide omega by this wave vector, then you are getting that the phase velocity is c by root over 1 minus omega p square by omega square, and refractive index, you know the formula, it is just like speed of light divided by phase velocity in the medium. So it is coming to be root over 1 minus omega p square by omega square. So as we told in our previous class that electromagnetic wave in the plasma, propagation depends on the kind of plasma that has been created. It may get attenuated or it can propagate. So for that, what we need to find out the plasma oscillation frequency, and plasma oscillation frequency, on which things it depend. So plasma oscillation frequency, this is omega p, that depends on the number density n, electronic charge, mass at the denominator. So mostly for electrons, you see that it will depend on the number density of that plasma that has been created. So if you have created a very high density plasma, N is very more, N is more, and then omega p also is more. So all those waves for which the frequency is greater than omega p, they will be passing, and for those whose frequency is less than omega p, they will get attenuated. So from this very simple kind of consideration and simplistic model, we find that plasma behaves as a refracting medium to electromagnetic waves, and whether it will propagate or not depends on the kind of plasma that you have created, and the phase velocity of that wave, basically that depends on your again plasma frequency and the frequency of the wave that is trying to propagate, and the refractive index depending on that, whether the wave will propagating in which path, whether it will be bent, and if it is bent, how it will be bent and in which direction. All these things you can determine from the kind of plasma that you have created. So this is about the detailed explanation of the derivation that we did on the last class. And here we need to know more about the plasma temperature. We already told that plasma temperature is usually a single quantity in most of the cases that we have learned so far. Like if I say that this room's temperature, I will not say that there are different temperatures in this room. Whatever temperature we will say that this is the temperature. This is the temperature in Mumbai, this is the temperature in Calcutta, or this is the temperature of this object. But when it comes to plasma, because of the different constituents of the plasma, because it is having electrons, neutrals and charged particles which are heavy in mass, like ions and double ions, molecular ions, all this. So they all respond in a different manner to electric fields, and usually we create plasma by discharge, electrical discharges, and they involve electric field, and the particles, basically the electrons, gain energy from the field only. And because the constituents, neutrals, are having no charge, they will not be able to gain enough energy from the field. Whereas the electrons being lighter, they will be gaining very quickly the energy from the electric field that has been applied over there. On the other hand, the ions also can gain energy from the field, but because they are bulky, they cannot move or pick up the energy very quickly. The other thing through which usually the equilibration in temperature achieves, at least they try to achieve, is the collision. Electrons are gaining energy from the field, they are colliding with the ions and the neutrals, and that way they are transferring their energy to the other particles. Now, if such collisions are very large in number, then there is a probability that they will equilibrate to a single temperature. But if it is not so, then there may happen that they are staying at different temperatures. So we explained that electrons will have much higher temperature compared to the ions and neutrals, and ions may have higher temperature compared to neutrals, and neutrals may have the lowest temperature. This kind of things happen because in many of the plasmas, the degree of ionization is sometimes less than 1%. Even less than 0.1%, 0.01% also happens in laboratory plasmas like the arcs. They are hardly ionized. So in those cases, such things are very, very much prominent, and especially in low pressure plasma where these electrons doesn't get enough chance to collide with the other particles to equilibrate the temperature. So they are the cases. Then we told that how the plasma temperature relates to the energy that is there. Then we came to the plasma equilibrium. Okay, so what we'll do actually, in the next class we'll start with this plasma equilibrium in a bit elaborate manner, and then we'll go for the plasma collision kinetics. Basically, it is the collision that tries to make the plasma reach the equilibrium, and we'll see in details how the collisions affects the plasma. Okay, so so far this much, and we'll come back in the next class.